Assalamu alaikum. Welcome to the next class. In the previous class, we derived the speed of the propagation of the wave. It comes out to be most exactly equal to the speed of the light, and the surge impedance for the different lines. So the overhead line was equal to 400 ohms, and for the cable it is equal to 40 ohms. And for cable it is 40 ohms only because of the capacitance of the cable is more as compared to the overhead line. When the capacitance is more, that's will be lower. Capacitance is more. There are two reasons: because the conductors uh, are very close to each other. Usually this capacitance is between capacitance and ground, and that sheath which is connected to the ground is also very close to the conductor. And also we know the capacitance is equal to 2 pi epsilon, where epsilon is equal to epsilon naught into epsilon r. The epsilon r for the overhead line is the epsilon r for the air, because the medium between the conductor and ground is air, and in case of cable the medium between conductor and the sheath is some dielectric which has ER more than that of the one. So in that case this capacitance is furthermore increased, so that's why it is very small as compared to this status C. So let us move ahead. We'll try to derive an expression for the voltage and current in a traveling wave. This is a section of the transmission line, and for a long transmission line we assume that this capacitance and inductance will be distributed. That's why the section has been, one of the sections has been taken like this. Let's say voltage at point X from the sending end is given as V, and the current flowing through the to this point will be equal to I. And when we move ahead by a delta X, so delta X will have its capacitance per unit length, delta it will have its inductance per unit length, and upon crossing it the current has changed by this much and the voltage has changed by this much. So the voltage at this point as a function of distance in x will be given by V of x and t, and I will be equal to small I x and t, function of x and t. The series voltage drop along the elemental length of the line can be expressed as, so delta V, that is the voltage drop across this element, will be equal to voltage of this minus voltage of this, that is voltage V of x of t, and the voltage at this point will be V of x plus delta x t, and that voltage will be equal to the voltage across the inductor, that is equal to L di by dt. The total inductance will be equal to this L into delta x di by dt. Here actually it is delta L and delta C. It means this is the elemental, small elemental inductance that usually we denote by small l, where L is the inductance per unit length. So whatever be the case for here, it will be L. So delta x, when L into delta x is multiplied, we get the total inductance of this section. So this is the total inductance di by dt. So this is the equation. We can say it's the KVL that we have used in this equation. Divide both sides with delta x, we get, so delta V delta xt by this delta x, Vxt minus Vx plus delta xt divided by delta x is equal to L di by dt. Now this L is here again equal to per unit value, inductance per unit length. So you can see when delta x tends to 0, this will go to the dv by dx, or del v by del x, since it's a partial derivative. And one more thing that you need to understand here, it will be minus d by dx, because usually d by dx is equal to v of x plus delta x minus v of x divided by dx. But here it is other way around. First it is v of x and then v of x plus delta x. So it will be minus d by dx is equal to L di by dt, or dv by dx, del v by del x to be precise, will be equal to minus L di by dt. This is, let us say, equation 1. Differentiate again equation 1 with respect to x, we get del square v by del x square is equal to minus L del square I by del x into del t. So this is equation 2. Similarly, current to charge the infinitesimal capacitance can be expressed as, so we can do the similar task and we can find out the value of this, because here I will be equal to this I, sorry, this I will be equal to this I of xt plus some delta x of t. So when doing the same exercise, we get this will be del I. Del I x of t by del x is equal to minus c del I x of t by del t. So sorry, this will be v by dt, because the current in the capacitance will be equal to c d by dx. Sorry, c d by dt. So this will be equal to dv x of t divided by dt. So del I by del x, here it should have been I, will be equal to c dv by dt. This is equation 3. Here you can please try to correct, this is v, and here I have forget to write down I. This is I. So differentiate the equation 3 with respect to t again. It will be equal to del square I divided by del x del t is equal to minus c del square v by del t square. So this is equation 4. I can equate the equation 2 and equation, this is del square v by del x square. Sorry, this is del square I by del x del t. This is del square I by del x del t. So I can put this equation over there, over here. So del square v by del x square is equal to minus L. This will be equal to minus C del square v by del t square. Del square v by del t. So it comes out to be minus and minus will be plus. Del square v by del x square will be equal to LC del square v by del t square. So I can write it like this: del square v by del x square minus LC del v square by del t square is equal to 0. I can divide LC both sides. It will be equal to 1 by LC del v square by del x square minus del v square by del t square is equal to 0. But we know that 1 by LC, 1 by root of LC will be equal to V. So 1 by LC will be equal to V square. So it will be equal to V square del V square by del x square minus del V square by del t square is equal to 0. Similarly, we can derive this equation for current as well. Del V square into del I square by del x square minus del square I by del t square is equal to 0. These two equations are used to find out the value of voltage and current with as a function of x and t. So let d is equal to d by dx and d dash is equal to d by dt. This actually exercise is to remind you what you have done in the previous classes, earlier classes. You have already the differential equation, partial differential equation. Otherwise, I will directly write down the result, but I want you to refresh it, and it may help you in refreshing that. So the equation can be written as v square d square minus d dash square into v is the voltage is equal to 0. Put d is equal to m and d dash is equal to 1, and the characteristic equation becomes v square m square minus 1 is equal to 0. So m is equal to plus minus 1 by v. So m1 is equal to 1 by v and m2 is equal to minus 1 by v. Its solution is given as v1 into v1 as a function of t plus x by v plus v2 as a function of t minus x by v. So this is t is the differentiation with respect to t, it is, and then this comes out to be with respect to x. This is multiplied, this coefficient is usually multiplied to x. This coefficient, that is 1 by v, is multiplied to x, and then I can simplify it to be equal to t into v plus x divided by v is equal to t into v minus x divided by v. When this happens to the property of the partial differential equation is that this v1 t plus x by v is same as v1 t plus x. Similarly, this would be same as v2 this v t minus x. And again, one more property of the partial differential equation is that v2 vt minus x will be same as v2 x minus tv. So I can write it like this. Finally, this will be v1 x plus vt plus v2 x minus. So final solution of this for the second order differential equation, the solution will be v1 x minus tv plus v2 x plus vt. This is the solution of this differential equation containing voltage, that is this whole equation. So while this v1, which is also can be denoted as vf, is known as forward traveling voltage wave or incident wave. So it is a traveling voltage from sending end to receiving end. So v2 is equal to backward traveling voltage wave, that's a reflected wave. Vf is also known as refracted wave. One more thing that I will like to make you clear here. Here, this point will act as a junction to this wave. Like you can see, when we For example, when a water wave is traveling and it happens sometimes some junction is there, and at that junction, or we can say some hurdlement is there, some water flows over that hurdle or that junction and some water flows back to that, and flowing over that junction means the refracted or incident water, and some flows back from that junction means the reflected water. Same happens to this wave, as this point, that is the receiving end, will act as a junction to this, and when this traveling wave hits this junction, some of the wave will travel to this load and some of the wave will hit back or reflect it back to this sending end. That is what is mean by, it is what is given by these two terms. That is, V1 is the forward traveling wave. It is a traveling wave which will go to the receiving end, and it is received by the receiving end. And this one, that is the backward traveling wave. After hitting the junction, this wave, some of the wave will be uh, will return back to the sending end. That is denoted by this V, 2x plus Vt. That is the backward traveling wave. So here you should note down that this Vf, that is the forward traveling wave, it is also known as incident wave and sometimes refracted wave. So we can call it as V of x of t is equal to Vf plus Vb. The value of the voltage wave at a given time t and a location x along the line is the sum of forward and backward traveling wave. Because at any point you can see now there are two waves which are which makes the total traveling wave. One is the forward, another is the backward. The relationship between traveling wave and the current can be expressed. Vf is equal to Zc into If. Because the traveling wave, it is traveling along the line, and it is when it travels along the line, this Zc appears as its impedance. And now it, because of this Zc, some current will also flow through this transmission line in the form of the traveling wave, and that forward current and the voltage will be uh, represented by this Vf is equal to Zc into If. Similarly, Vb is equal to the backward traveling wave is equal to minus Zc into Ib, because in this case it is minus because now this current Ib will be flowing to the backward end. At any point, this backward voltage will be equal to minus Zc into Ib, because the direction of the current will be now reversed. Well, Zc is the characteristic impedance of the line. So from here, If is equal to Vf by Zc and Ib is equal to minus Vb by Zc. And we would have derived the same equation if we have solved this equation, but we want to use this equation and this equation to derive it from the current I. And when we have derived it, this equation, when we have solved this equation, we have got the current in terms of If and Vf. Now here we'll get it in terms of Vf and Vb. So If plus Ib will be equal to Vf divided by Zc. You can see it from here. This is If plus Vb, where If is equal to I into x minus Vt and Ib is equal to I into x plus Vt. So, but I want to calculate them in terms of Vf and Vb. This is Vf by Zc minus Vb by Zc, which is equal to 1 by Zc Vf minus Vb. So Ifxt will be equal to 1 by Zc V1 x plus Vt, which is Vf minus Vf x minus Vt, V2 x minus Vt, which is Vb. This should have been x minus Vt minus V2 x plus Vt, because backward traveling here we have plus and forward traveling we have minus. Please try to correct it. From equation this, I into Zc will be equal to Vf minus Vb. This is Vf minus Vb, and V is equal to Vf plus Vb. This is already from equation 8. So adding these two equations, that is V plus I Zc will give us Vf. So V plus I into Zc divided by 2 will be Vf. Subtracting these two, we get B2 Vb. So Vb is equal to V minus I into Zc divided by 2. This equation we have already derived in power system first in this chapter. I remember is the what was that chapter? Performance of the transmission line. For long transmission, we have derived this equation there also. So forward traveling wave is V plus I into Zc divided by 2, and backward traveling V minus I into ZC divided by 2, where V is the incident wave at the junction, I is the incident current at the junction. Similarly, for this case, that is the characteristic impedance. Now, effect of the line termination. What will happen when we have different terminations? Let us say the line is terminated by Z. That means junction is an impedance. So receiving voltage will be equal to V is equal to I into Z. These two are both are incident voltage and incident current. This is the load impedance. Substituting the equation 15 into 13, we get what is Vf equal to V into I into ZC divided by 2, where V is equal to I into Z. Now this will be Vf is equal to I into Z plus I into ZC divided by 2. That is I into Z plus I into ZC divided by 2. It comes out to be equal to, here when we calculate I into Z plus ZC divided by 2 twice Vf divided by Z plus ZC is equal to I. That is what this equation means. Okay, put equation 16 into 15. This equation has to be put in this. So V is equal to twice Z divided by Z plus ZC into it. This is the incident voltage in terms of forward voltage. So the incident voltage comes out to be this one. Okay. Now, also VB is equal to V minus I into ZC divided by 2. That means now V is equal to I into Z minus I into ZC divided by 2. That is I into Z minus ZC divided by 2. So I will be equal to twice VB divided by Z into Z. Put the value of I from 16 into 18. Now I is also equal to this value. I is also equal to this value. So we have to equate these two equations. Twice Vf divided by Z minus Z plus ZC is equal to twice VB divided by Z minus ZC. This and this will cancel out. So VB in terms of Vf will be equal to Z minus ZC divided by Vf. So this is the backward traveling voltage wave or reflected voltage wave in terms of the forward traveling voltage wave. Similarly, we can calculate this I is equal to in terms of IF twice ZC divided by twice ZC divided by Z plus ZC, because if you see here, not in this case, I is equal to twice Vf divided by Z plus Zc, where Vf is equal to If into Zc from this equation. Vf is equal to If into Zc. When we put up here If into Zc, it comes to twice Zc divided by Z plus Zc into If. Similarly, for Ib, you can put the value of here Vb is equal to minus Ib Zc, Vf is equal to If Zc. So putting the value of there, you can get If is equal to Ib is equal to minus Zc Z minus Zc divided by Z plus Zc into If. This is the reflected current. So these coefficients, that is, one is this one twice Z divided by Z plus Zc, Z minus Zc divided by Z plus Zc, twice Zc divided by Z plus Zc, and minus Z minus Zc divided by Z plus Zc. They are named separately. The twice Z divided by Z plus Zc, this is actually the this coefficient which relates the incident wave and the forward traveling wave. That is known as the refraction coefficient of the voltage, denoted by alpha V. Similarly, this coefficient which relates the forward current, incident current, and the forward, yes, this incident voltage and the forward traveling current, that is known as the refraction coefficient of the, this should have been current here. It's not voltage, this is current. That is alpha I. From here, they are related to each other. Alpha V plus alpha I is equal to 2. You can calculate them twice Z divided by Z plus Zc plus twice Zc divided by Z plus Zc. They comes out to be equal to 2. This is always the case. When we have the value of alpha I, you can calculate value of alpha V. 2 minus alpha I is equal to alpha V. Or similarly, if you have alpha V, you can subtract that alpha V from 2. You can get the value of alpha I. So these are related like this. Z minus Zc divided by Z plus Zc, reflection coefficient of voltage, that is beta V, and minus Z minus Zc divided by Z plus Zc is a reflection coefficient of the current beta I. So beta V plus beta I is equal to 0, and you add them to add up to 0, or beta V is equal to minus times beta I. So when the relation which with each other, you remember, you can calculate one and other will be calculated by these two equations. So when line is terminated by Zc, that is the characteristic impedance. This is very important. When Z is equal to Zc, that is line is terminated by Zc, alpha V is equal to, you can see, Alpha V is 1 is ZC, this is ZC, twice ZC divided by twice ZC will be equal to 2. This is ZC, this is ZC, twice ZC by twice ZC will be, sorry, twice ZC. This is 1 and this is 1. Refraction coefficient is 1 here, refraction coefficient is 1 here. It will ZC minus ZC, ZC plus ZC will be 0, this will also be 0. That's what I have written over here. So Vf is equal to V. What is the forward voltage V? Same is the incident voltage V. What is the forward current? Same is the incident current. Vb is equal to 0, Ib is equal to 0. When the line is terminated by characteristic impedance, reflection in the voltage and current will be 0. What does this mean? It means the line will behave as an infinite line as if there is no junction. Even if there is junction, and where we have put an impedance of Zc, but when that Z is equal to Zc, it behaves an infinite line as if there is no junction from 0 to infinity. So there will be no reflection of the voltage or current. When the line is terminated by R, it's very simple. You just have to replace Z by R. So V will be equal to twice R divided by R plus Zc because that will be equal to R. I will be equal to twice Zc divided by R plus Zc because here Z is equal to R again. And similarly, Vb and Ib, they are in both the equations. You can see that R is replaced by, sorry, Z is replaced by R. This is the only difference. Now, another junction is the short circuit line. When the line is short circuit, in that case, this Z will be equal to 0. So alpha V is equal to twice Z divided by Z plus Zc. This is comes 0. There will not be any refraction. There will be no incident voltage V, or we can say simply the voltage at the receiving will be 0. Alpha I, that is twice Zc divided by Z plus Zc. Z is 0. That is Zc will cancel. It comes to highest refraction of the current. All the current will be at the receiving end. That is, the current will have a good amount of magnitude. This tells us the idea how current will behave at the receiving end, voltage will behave at the receiving end. This 2 means the high value. Beta V, the reflected voltage, Z minus Zc, since this is 0, minus Zc by Zc will be minus 1, and reflected current will be minus of this, it will be equal to 1. So there will be a reflection in the current, but with the positive value. Here will be a reflection of the voltage, but with negative value. I will try to show you pictorially so that it may be slightly understood to you. Now this P is equal to 0 plus means at the sending end, and length of the line is L. And we assume that current and voltage are like this, and they are of step nature, step wave nature. This is step wave at the sending end. This is the step wave voltage at the sending end. So when they travel at the receiving end, they will travel at I. It will travel at V like this. This will travel at almost all the current will be received from the receiving end, and all the current voltage will be received at the receiving end. Now, what will happen at this receiving end depends upon what type of junction we have, whether we have Z, whether we have R, whether we have short circuit, open. Since we have a short circuit, there will be a reflection to the current, there will be a reflection to the reflection to the current as well as reflection to the voltage. You can see that since the reflection to the current is, what is the reflection to the current is plus 1. That is why there will be a 2i that is reflected back. Actually plus 1 already, and now the one more plus 1, that is 2i. Now, sorry, it is not for this. Now what is the reflection voltage? The reflected voltage is minus 1. So minus V will be reflected back to the sending end. When minus 1 will be reflected back to sending end, at every, you can see that we have 0 voltage, and at the receiving end we will have the 0 voltage, and when it is reflected back to the sending end, here the current is building up. The current is building up. When the current will go back to the sending end, it has reached to the 2i, and after that you will see that if we keep on seeing the reflections, here it will reflect back with a positive current, it will be 3i, it will be reflected back with the positive, it will be again V, and then this will happen. You will see that the total current will build up depending upon the voltage and the impedance of the light, and the total voltage will automatically will swing back and forth, and total voltage will be at the receiving end will be ultimately equal to 0. This is the pictorial view of the voltage and current wave and how they will behave when a short circuit occurs at the terminal, or we can say the junction is the short circuit. Let us see what will happen when the junction is an open circuit. That is infinity. When that is infinity, in this case, alpha v will be equal to 2. Alpha v will be equal to 2. So you just have to put a limit z tend to infinity to z divided by z plus zc. So it will be equal to 2. Try to find out this limit, it will become out to be 2. So highest refraction, the alpha is this value. When z is infinity, zc is some finite value, it comes out to be 0. Voltage will be reflected back also, beta v, z minus zc divided by z plus zc. So z is infinity, it comes out to be equal to minus plus 1 here. In this case it is plus 1, and beta I is minus times of this, it will be minus I. So this also has been shown pictorially. The first diagram where we have assumed current and voltage to be of step nature, so they remain the same, and when they reach the junction they remain as it. This is I and current, this is similar to that of this, but when they see the junction the reflections will be different. Current will have a reflection of -1, you can see reflection of the current is -1, but the reflection of the voltage will be +1. So voltage will build up in the open circuit, that's why the open circuit voltage for a long transmission line will have more as compared to the sending in. We can say that is the front effect. This also tells us the same. When it is reflected back, the current will totally be equal to 0, because the summation of these two will be the total current will be equal to 0. Here the voltage has reflected back with the positive magnitude, and total voltage will come out to be equal to 2. It means the voltage is building up to a higher value depending upon the value of the voltage and the capacitance present in the circuit. So this is how the pictorially the short circuit and open circuit can be demonstrated. Now the conclusion: when a line is terminated with a characteristic impedance, that is z is equal to zc, the beta v, that is the reflected voltage and reflected current, will both be 0. Then vb and ib, reflective voltage coefficient, reflected current coefficient will be 0. Thus vb and ib is equal to 0, that is there will be no reflection of voltage and reflection current. In other words, the line will act as if it is a infinitely long line, as if there is no junction present at any point of the line. That is what is meant by infinitely long. Second thing, when the line is terminated with an impedance z is greater than zc, then the vb is positive and ib is negative, and z is greater than zc. When z is greater than zc, so this beta v is positive, so vb is positive, and this will be negative because it's a negative of this. Therefore, the reflected surge consists of increased voltage and reduced current. In that case, voltage will increase and current will reduce. When the line is terminated with an impedance Z is less than Zc, then Vb is negative and Ib is positive. Therefore, the reflected surge consists of decreasing the voltage and increasing the current. I hope you understood it. Thank you. I'll stop here.